First of all, I'd like to talk why I chose this. My first intention was not to do a quantum mechanics or something like this style research paper, but I I really thought that
It's okay, you say agree now.
I really thought that the essence of the origin was more like father in space or that. But Pera told me that there were other kinds of science that studied the same thing but from another point of view. And I really felt more attracted to this topic. Most of all because of those two questions that have made my head go upside down completely. First of all, it's why looking deeper and not more outside. As I said, I was thinking about space, and maybe it's just in front of me everywhere. And why is it true or is it probable? What I've got to do an abstraction process I've had to do because nothing is true in quantum mechanics. Something is probable to happen. You have more probability, less probability. Never true because if you look at it, it's not true anymore. It's just you have to believe. It's a faith leap that not everyone is really ready to assume. Me either. So, okay, second, my objectives for this project were very easy, really, although they coasted a little bit. First of all, was learning how the games works. Games is a program I've used for doing my practical part. And second, using this program, calculating the ionization energy of the 10 first elements. This has been really tough, more than I thought, but it has been really nice in the end.
Wow.
Third, my research paper, the written edition, is very simple. It just goes chronological. First of all, I talked about some Greek philosophers who really talked about the atom and all those concepts. And then I introduced the first atomic models that were created to respond to these questions. Second, I talked about the 5 big theories that bring to the atomic model we have now, that are Werner Heisenberg uncertainness theory, Erwin-Schrödinger equation, photoelectrical effect from Albert Einstein, energy quantum by Max Planck, and the atomic model from Niels Bohr. Then I explained that model according to these theories, and finally I did my most difficult part, that was the modern one, that was researching about digital atomistic calculation methods. It's very difficult because there's no really very contrasted information, and sometimes they have different opinions and different points of view that don't help to do a research project like this. And in the end, I proved the program and all that stuff. My methodology, as I said, has been using this program, the WIN games, that games means General Atomic and Molecular Electronic Structure System. What it does is working with an information I give to it, and it gives an output data that gives me the information I want to know the atom's properties. It's not in the paper, I just read it and I have to do my calculations to get to that. Well, the input file I get is this one. I put the things that I can modify to get it into the program. First of all, the multiplicity and the charge that allow the program to know what aspect of the atom I want to work with. Maybe I want to work with something that has electrical interactions and something with something that it doesn't work with anything, it's just it. Then the title of what I'm doing, the name of the atom I'm working with, and this is the Gaussian functions that are, how would I say, I think that the area of the space where it's more probable to find electrons. And it's by the Schrödinger function, it's a not exact solution, but it's the most approximate because, as many of you know, this Schrödinger equation has no solution, only for the hydrogen atom. Then it worked like, I'm sorry, I don't get enough what. I don't mind, I translate it. The one that is between bars is what the program does, and this is what I get. First of all, there's the input data that I showed before. It gets inside and it gets a transformation into something the program can read. Then the Hartree-Fock equations are applied to disclose all this information. In the end, I get a first energy with total energy, orbital energy, and a wave function. Then it does a lap again into the program to compare the two results. If it changes, it does it again. But when it coincides, we get to the next step. That's the output data. That's what I read when I finish. And we found two words that are very typical in this area that are density converged. When density converges, the results you get are reliable. This is what I get, well, two parts of what I get. I've got output data of 90 pages actually. What I have to find is these, between all those numbers, and it's very difficult sometimes. The first I see, as I said, is I check that the density has converged, because if not, if it doesn't converge, my results are not reliable. I can use them for the calculation. Then the main thing that I've focused in this research paper is this. This is the energy of the atom I'm working with. It tells me the total energy that it has. This is what I've used to work with the properties I've calculated. And then we have this, it's a more technical part, which you can identify the different kinds of orbitals that this has. And finally I got results from everything I did, of course. First of all, the ionization energy was really nice. It was really coincident in the hydrogen was exact, as I said. Schrödinger equation has a solution for the hydrogen, but for the rest, we only got a little mistake, like there's a 13.7%, not more. This is 10% actually, but it's because it has more weight and things used to have a bigger size and more mistake. This is the electronic affinity. It's another property that I calculated, and I've got several problems with it because I couldn't get some results. So I really have to do what I could with this. I know where the mistake was, but I didn't have time to solve it. The mistake was that I was giving the programming information that went farther than the limits it could. What I could do was modifying the program to make my limits bigger so my new information can get inside it. But this was a proof we wanted to do to see how big the mistake was. We didn't expect that much, of course, but it really is. And as a conclusions, I've really loved to do this topic because it's what I'm really interested about to do in the future. But I've also learned many new things about this area of science completely. The main thing that I've got with this project was twisting my mind upside down, because nothing that I knew was really true, or according to my information that I've got, it wasn't really relevant. So I had to change my point of view and do what I could. And